Right now, at this very moment, 8 major planets are moving through space in paths they have traced billions of times before. Each one follows an ellipse so precisely calculated by gravity that we can predict their positions thousands of years into the future. Venus will rise tomorrow morning exactly when the mathematics say it will. Jupiter's Great Red Spot will continue its slow rotation in the southern hemisphere, just as it has for at least 190 years. Saturn's rings will catch sunlight at the same angle they caught it yesterday, and the day before, and 10,000 days before that. There is something deeply calming about this constancy. While everything in our immediate experience seems to change and shift, these worlds maintain their ancient rhythms with a reliability that transcends human timescales. They are not rushing anywhere. They are not late for anything. They simply exist in motion, held in balance by forces that have remained essentially unchanged since the solar system settled into its current configuration more than 4 billion years ago. Tonight, we are going to explore facts about planets that share this quality of calm permanence. We will move slowly through the solar system, visiting each world not as a tourist rushing through highlights, but as someone settling in to understand the quiet details that make each planet what it is. We will talk about orbital mechanics and atmospheric compositions, about magnetic fields and rotation rates, about the patient geological processes that shape surfaces over millions of years. This is not a journey that requires your full attention. You can listen actively, absorbing the information and building a mental picture of these distant worlds. Or you can let the words wash over you, allowing your mind to drift among planets and moons while your body relaxes into rest. There are no quizzes, no points you must remember. This is simply an opportunity to spend time with facts that are, by their nature, soothing in their stability and permanence. We will cover substantial ground tonight. The script ahead is designed to last approximately 2 hours, giving you plenty of time to explore, to rest, or to sleep. The pacing will remain gentle throughout. New information will be introduced gradually with context and explanation. Nothing will be rushed. If you find yourself drifting away from the words, that is perfectly fine. The planets will still be here, following their orbits when your attention returns. Before we begin moving through the specific worlds, it helps to understand the fundamental framework that governs all planetary motion. This framework was discovered over centuries by astronomers who looked up at the night sky and tried to make sense of the wandering points of light that did not behave like stars. Those astronomers eventually realized that planets move according to laws, not whims, and that these laws can be expressed in mathematics beautiful enough to inspire wonder and simple enough to provide comfort. The solar system is approximately 4.6 billion years old. It formed from a cloud of gas and dust that collapsed under its own gravity, creating a spinning disk with the young sun at its center. Within this disk, particles collided and stuck together, gradually building up larger and larger objects. First came planetesimals, bodies perhaps a kilometer or so across. Then came protoplanets, growing through continued collisions. Eventually, the largest of these became the planets we observe today. This process took tens of millions of years, which sounds like a long time until you compare it to the age of the solar system as a whole. The formation period represents only about 1% of the total history. For the remaining 99%, the planets have been largely in their current configuration, orbiting the Sun in the same basic paths, slowly evolving but never fundamentally changing their roles in the cosmic architecture. 8 planets now orbit the Sun. 4 are rocky worlds, relatively small and dense, with solid surfaces you could theoretically stand on. 4 are giant planets, massive worlds composed primarily of hydrogen, helium, and other volatile compounds with no solid surface to land upon. Each planet occupies its own distinct zone in the solar system, separated from its neighbors by distances that dwarf anything we experience in daily life. Mercury orbits closest to the Sun, completing one trip around our star every 88 Earth days. It is a small world, only slightly larger than Earth's moon, with a surface heavily cratered from billions of years of impacts. Mercury has almost no atmosphere to speak of, just a thin exosphere of atoms knocked off its surface by the solar wind and micrometeorite impacts. During the day, its surface temperature can reach 430 degrees Celsius. At night, it can drop to minus 180 degrees Celsius. This extreme temperature variation happens because Mercury rotates very slowly and has virtually no atmosphere to distribute heat. But here is something quietly remarkable about Mercury's rotation. It is locked in what is called a 3-to-2 spin-orbit resonance with the Sun. This means that for every 2 orbits Mercury makes around the Sun, it rotates on its axis exactly 3 times. This is not a coincidence or a random occurrence. It is the result of tidal forces from the Sun acting on Mercury's slightly elliptical shape over billions of years, gradually slowing its rotation until it settled into this stable pattern. The consequence of this resonance is peculiar. If you were standing on Mercury's surface, you would experience a day that lasts 176 Earth days, which is exactly 2 Mercurian years. The Sun would rise, move across the sky with unusual slowness, pause, and move backward briefly due to Mercury's elliptical orbit, then continue forward again before finally setting. Then would come 176 Earth days of darkness before the next sunrise. This is not chaos. This is orbital mechanics creating a pattern so stable that it will continue essentially unchanged for billions of years to come. Venus orbits next, at a distance of roughly 108 million kilometers from the Sun. It is almost the same size as Earth, with a diameter of 12,104 kilometers compared to Earth's 12,742 kilometers. For this reason, Venus is sometimes called Earth's sister planet, though the 2 worlds have evolved in dramatically different directions. Venus rotates extremely slowly, taking 243 Earth days to complete one rotation on its axis. It also rotates in the opposite direction from most planets, a phenomenon called retrograde rotation. If you could stand on Venus's surface and survive the crushing atmospheric pressure and extreme heat, you would see the Sun rise in the west and set in the east. The combination of slow retrograde rotation and orbital motion means that a solar day on Venus, the time from one sunrise to the next, lasts 117 Earth days. No one is entirely certain why Venus rotates backward. The most widely accepted explanation involves gravitational interactions with the Sun and Venus's extremely thick atmosphere during the planet's early history. Tidal forces from the Sun can, over billions of years, slow down a planet's rotation and even reverse it if conditions are right. Venus may have started with a normal rotation and gradually slowed down, stopped, and reversed, or it may have been knocked into retrograde rotation by one or more massive impacts early in solar system history. We do not know for certain, and that uncertainty does not diminish the calm fact of Venus's current state. It rotates slowly backward, and it will continue to do so for as far into the future as we can meaningfully predict. Earth comes next, and you know Earth well. It orbits at a distance of approximately 150 million kilometers from the Sun, a distance so commonly referenced in astronomy that it has its own name, 1 astronomical unit, or AU. Earth takes 365.25 days to orbit the Sun, which is why we have leap years every 4 years to keep our calendar aligned with the seasons. Earth rotates once every 23 hours, 56 minutes, and 4.1 seconds relative to the distant stars. We round this to 24 hours for practical purposes, but the actual rotation period is slightly shorter. Earth's rotation is gradually slowing down due to tidal interactions with the Moon. Every century, the length of a day increases by about 1.7 milliseconds. This is not something you would ever notice in a human lifetime, but over hundreds of millions of years, it becomes significant. Fossil evidence from ancient corals and shells, which grow in daily and seasonal patterns, shows that days were shorter in the distant past. About 450 million years ago, during the Ordovician period, a year contained approximately 422 days, each about 21 hours long. The Moon was also closer to Earth then, and has been slowly drifting away at a rate of about 3.8 centimeters per year due to the same tidal forces that slow Earth's rotation. This process will continue far into the future. Billions of years from now, if Earth still exists, the day will have lengthened considerably and the Moon will have drifted much farther away. Eventually, Earth's rotation period and the Moon's orbital period will match, creating a situation where the same side of Earth always faces the Moon, just as the same side of the Moon currently always faces Earth. This is called mutual tidal locking, and it represents a stable endpoint toward which the Earth-Moon system is very slowly evolving. Mars orbits beyond Earth, at an average distance of about 228 million kilometers from the Sun, or 1.52 AU. Mars is smaller than Earth, with a diameter of 6,792 kilometers, about half Earth's diameter. It rotates at almost exactly the same rate as Earth, with a day, called a sol by Mars researchers, lasting 24 hours and 39 minutes. This similarity in day length is purely coincidental, but it makes Mars feel somehow more familiar than worlds with radically different rotation periods. Mars has seasons, just like Earth, because its axis is tilted at about 25 degrees, very close to Earth's 23.5-degree tilt. However, Martian seasons last almost twice as long as Earth's, because Mars takes 687 Earth days to complete one orbit around the Sun. Spring in Mars's northern hemisphere lasts about 194 sols. Summer lasts 178 sols. Autumn lasts 142 sols, and winter lasts 154 sols. The seasons are not equal in length because Mars's orbit is more elliptical than Earth's, and the planet moves faster when it is closer to the Sun and slower when it is farther away, in accordance with Kepler's second law of planetary motion. The Martian atmosphere is thin, about 1% the density of Earth's atmosphere at sea level, and it is composed primarily of carbon dioxide, about 95%, with small amounts of nitrogen and argon. This thin atmosphere cannot retain much heat, so while daytime temperatures at the equator can reach a comfortable 20 degrees Celsius during summer, nighttime temperatures regularly plunge to minus 73 degrees Celsius or lower. The temperature variation between day and night is extreme because there simply is not enough atmospheric mass to store and redistribute heat. Despite the harsh conditions, Mars is geologically fascinating in ways that unfold slowly, across time. The planet has the largest volcano in the solar system, Olympus Mons, which stands about 21.9 kilometers high, roughly 2.5 times the height of Mount Everest above sea level. Olympus Mons is a shield volcano, built up gradually over millions of years by lava flows that spread out in broad, gentle slopes. It is no longer active today, as far as we can tell, but it stands as a monument to volcanic processes that once shaped significant portions of the Martian surface. Mars also has a canyon system called Valle Marineris that stretches about 4,000 kilometers long, up to 200 kilometers wide in places, and reaches depths of 7 kilometers. If placed on Earth, it would span nearly the entire width of the United States. This canyon was not carved by water, but likely formed through a combination of tectonic activity and the collapse of crustal material. It exists in the same quiet, patient state it has existed in for billions of years, slowly eroding under the influence of dust storms and temperature changes, but not changing in any dramatic way. We now cross a significant gap in the solar system, moving from the terrestrial planets to the realm of the giants. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky bodies left over from the solar system's formation. These asteroids orbit the Sun in much the same way planets do, following elliptical paths governed by gravity. The largest asteroid, Ceres, is about 940 kilometers in diameter and is classified as a dwarf planet. Despite popular depictions in movies, the asteroid belt is mostly empty space. If you were traveling through it, you would rarely see asteroids close enough to appear as anything more than distant points of light. Jupiter is the first of the giant planets and the largest planet in the solar system. It orbits at an average distance of about 778 million kilometers from the Sun, or 5.2 AU. Jupiter is massive, containing about 318 times the mass of Earth. Its diameter at the equator is about 143,000 kilometers, which means you could fit over 11 Earths side by side across Jupiter's equator. Despite this enormous size, Jupiter rotates faster than any other planet in the solar system, completing one rotation in just 9 hours and 56 minutes. This rapid rotation creates a powerful centrifugal effect that causes Jupiter to bulge noticeably at its equator. The equatorial diameter is about 9,000 kilometers larger than the polar diameter. You could measure this difference with careful observation and mathematics, and astronomers have been doing so for centuries. The bulge is not a defect or an irregularity. It is a natural consequence of rotation, a shape that balances the inward pull of gravity with the outward push of rotational motion. Jupiter's fast rotation also organizes its atmosphere into distinct bands of clouds that run parallel to the equator. These bands are regions of differing wind speeds and directions, created by the combination of rapid rotation and heat rising from Jupiter's interior. The lighter-colored bands are called zones, and they are regions of upwelling gas where ammonia ice crystals form at high altitudes, creating bright white clouds. The darker bands are called belts, and they are regions of descending gas where we see deeper into the atmosphere, revealing warmer, darker clouds below. The boundaries between zones and belts are locations of powerful winds and turbulence. Wind speeds in Jupiter's atmosphere can exceed 500 kilometers per hour, though these winds are remarkably consistent over time. Observations from spacecraft and telescopes show that Jupiter's banded structure remains stable year after year, decade after decade. The exact positions and widths of individual bands can change slightly, but the overall pattern persists. This is not weather in the way we experience it on Earth, with storms that come and go in days. This is atmospheric circulation driven by heat and rotation, operating on a scale and time scale far beyond human experience. The most famous feature of Jupiter's atmosphere is the Great Red Spot, an anticyclonic storm larger than Earth itself. The spot is oval-shaped, currently measuring about 16,000 kilometers across at its widest point, though historical observations show it has slowly shrunk over the past century and a half. In the 1800s, when telescopic observations became precise enough to measure it reliably, the Great Red Spot was about 40,000 kilometers across. The shrinking appears to be gradual and may represent a natural long-term variation in the storm's structure. The Great Red Spot rotates counterclockwise, completing one rotation every 6 to 7 days. It sits in Jupiter's southern hemisphere at about 22 degrees south latitude, embedded in a region where eastward and westward jet streams create a stable environment for the storm to persist. The reddish color likely comes from complex organic molecules called tholins, created when sunlight breaks apart simpler molecules in Jupiter's upper atmosphere. These molecules then drift down and get caught up in the storm's circulation. We know the Great Red Spot has existed for at least 190 years because we have continuous telescopic observations dating back to the 1830s. It may be much older than that. Earlier astronomers, including Giovanni Cassini in the 1600s and Robert Hooke in the same century, reported seeing large spots on Jupiter that might have been the same feature, but the observations are not detailed enough to be certain. What we can say with confidence is that the Great Red Spot is persistent in a way that defies comparison with any weather system on Earth. Earth's most powerful hurricanes last days or weeks. Jupiter's Great Red Spot has lasted centuries, sustained by the planet's internal heat and the dynamics of its atmosphere. Jupiter emits more heat than it receives from the Sun. Measurements show that Jupiter radiates about 1.6 times as much energy as it absorbs from sunlight. This extra heat comes from the gradual contraction of the planet under its own gravity. When Jupiter first formed, it was larger and hotter than it is today. As it radiated heat into space, it contracted slightly, and that contraction released gravitational potential energy as heat. This process is still happening today, very slowly, making Jupiter a gently cooling ember of its formation. This internal heat drives much of Jupiter's atmospheric activity. It creates convection currents that rise from deep within the planet, carrying heat upward and organizing the clouds into the bands we observe. Without this internal heat, Jupiter's atmosphere would be much calmer, more dominated by the relatively weak input of solar energy at 5 AU from the Sun. Instead, Jupiter's atmosphere is dynamic and active, but in a stable, long-term way that has remained essentially unchanged throughout human history. Jupiter has at least 95 known moons, and more are discovered occasionally as telescopes and techniques improve. The 4 largest moons, discovered by Galileo Galilei in 1610, are called the Galilean moons: Io, Europa, Ganymede, and Callisto. Each is a world unto itself, with its own geology and history. Io is the innermost of the Galilean moons and the most volcanically active body in the solar system. It orbits Jupiter every 1.77 days at a distance of about 422,000 kilometers. Io is caught in a gravitational tug-of-war between Jupiter and the other Galilean moons, particularly Europa and Ganymede. This creates tidal forces that flex Io's interior, generating heat through friction. That heat powers hundreds of active volcanoes that constantly resurface the moon, giving it a yellow and orange mottled appearance from sulfur and sulfur dioxide compounds. Despite all this volcanic activity, Io's eruptions follow patterns. The largest volcanoes are located at specific latitudes and longitudes, determined by the internal structure and the pattern of tidal heating. Spacecraft observations show that some volcanic centers have been active for decades, erupting regularly or semi-regularly. This is dynamic geology, yes, but it operates within a framework of gravitational physics that is entirely predictable. Io will continue to be volcanically active for as long as it remains locked in its current orbital configuration with Jupiter and the other moons. Europa orbits next, at a distance of about 671,000 kilometers from Jupiter, completing one orbit every 3.55 days. Europa is covered in water ice, and beneath that ice, scientists believe there is a global ocean of liquid water that may be 100 kilometers deep or more. This ocean exists because tidal heating from Jupiter keeps Europa's interior warm enough to maintain liquid water, despite surface temperatures that hover around -160 degrees Celsius. The ice shell covering Europa's ocean is crisscrossed with linear features called lineae, which appear to be cracks and ridges in the ice. These features suggest that the ice shell is geologically active, breaking and shifting over time as the ocean beneath flexes under tidal forces. Some models suggest the ice shell may be only 10 to 15 kilometers thick in places, while others suggest it could be 25 kilometers or more. We do not know for certain, but we do know that Europa represents one of the most promising locations in the solar system to search for life beyond Earth, precisely because of this stable subsurface ocean that has likely existed for billions of years. Ganymede is the largest moon in the solar system, with a diameter of 5,268 kilometers, larger than the planet Mercury. Ganymede orbits Jupiter every 7.15 days at a distance of about 1,070,000 kilometers. It is the only moon in the solar system known to have its own magnetic field, generated by a liquid iron core that remains molten due to residual heat from formation and possibly some tidal heating. Ganymede's surface shows two distinct types of terrain: dark, heavily cratered regions that are billions of years old, and lighter, grooved terrain that is somewhat younger and shows evidence of tectonic activity. The grooved terrain consists of parallel ridges and valleys that extend for hundreds of kilometers, likely formed by tectonic stretching and cracking of the icy crust. Like Europa, Ganymede is believed to have a subsurface ocean, buried beneath a thicker ice shell, perhaps 150 kilometers deep. Callisto orbits farthest from Jupiter among the Giunsu Galilean moons at about 1,883,000 kilometers, completing one orbit every 16.7 days. Callisto is heavily cratered, with one of the oldest surfaces in the solar system, showing little sign of geological activity. It appears to have avoided the tidal heating that affects the inner moons, possibly because it is not locked into the same orbital resonances. Callisto may also have a subsurface ocean, though evidence is less direct than for Europa and Ganymede. These four moons exist in a state of orbital resonance. For every one orbit Ganymede makes around Jupiter, Europa makes exactly 2, and Io makes exactly 4. This is called the Laplace resonance, named after the mathematician Pierre-Simon Laplace, who studied it in the 1700s. This resonance is stable and self-reinforcing. If one moon drifts slightly out of sync, gravitational interactions pull it back into alignment. This pattern has persisted for billions of years and will continue far into the future. Beyond Jupiter lies Saturn, orbiting at an average distance of about 1.4 billion kilometers from the Sun, or 9.58 AU. Saturn is the second largest planet, with an equatorial diameter of about 120,000 kilometers. Like Jupiter, Saturn is composed primarily of hydrogen and helium, and like Jupiter, it emits more heat than it receives from the Sun, about 2.3 times as much. This excess heat comes from both gravitational contraction and a unique process where helium rain forms in Saturn's interior and releases heat as it falls toward the core. Saturn rotates rapidly, completing one rotation in about 10 hours and 33 minutes. Though measuring Saturn's rotation is surprisingly difficult because the planet has no solid surface and different parts of the atmosphere rotate at different speeds. The number I just gave you comes from measuring periodic variations in Saturn's radio emissions, which are linked to the rotation of the planet's magnetic field and presumably the deep interior. Saturn is most famous for its magnificent ring system, the most extensive and visible ring system of any planet. The rings are composed primarily of water ice particles ranging in size from tiny grains smaller than sand to boulders several meters across. The ring system extends outward from about 7,000 kilometers above Saturn's equator to about 80,000 kilometers, but is remarkably thin, in most places only about 10 to 100 meters thick. This thinness is maintained by constant collisions between ring particles. When particles collide, those moving above or below the ring plane lose energy and settle back toward the plane. Over time, this creates a flat, disc-like structure. The rings are not solid. They are composed of billions of individual particles, each one orbiting Saturn independently according to Kepler's laws. Particles closer to Saturn orbit faster than those farther out, creating the appearance of rotation when viewed from a distance. The rings are divided into several main sections, designated by letters in the order they were discovered: the D, C, B, A, F, G, and E rings. The B ring is the brightest and most opaque, while the C ring is fainter and more translucent. The A ring is separated from the B ring by the Cassini division, a gap about 4,700 kilometers wide, first observed by Giovanni Cassini in 1675. The Cassini division is not completely empty, but it contains fewer particles than the surrounding rings. This gap is maintained by gravitational resonances with Saturn's moon Mimas. Particles in the Cassini division orbit Saturn at a rate that is exactly half the orbital rate of Mimas, meaning they complete one orbit for every 2 orbits Mimas makes. This creates a resonance where the gravitational pull of Mimas occurs at the same point in each orbit, gradually perturbing particles and clearing them out of the region. Other gaps in the rings are maintained by small moons that orbit within the ring system itself, called shepherd moons. These moons gravitationally interact with ring particles, clearing gaps and creating sharp edges. The F ring, which orbits just beyond the A ring, is particularly influenced by 2 shepherd moons, Prometheus and Pandora, which orbit on either side of the ring and keep it confined to a narrow band. The origin of Saturn's rings is still debated among planetary scientists. One possibility is that they are remnants from the formation of the solar system, material that never coalesced into a moon because it was too close to Saturn and tidal forces prevented accumulation. Another possibility is that they formed more recently, perhaps when a moon or large comet ventured too close to Saturn and was torn apart by tidal forces. Studies of the ring's mass and composition suggest they may be relatively young, perhaps only a few 100 million years old rather than 4.6 billion years old like the solar system itself. This remains an area of active research, with data from the Cassini spacecraft providing new insights. Saturn has at least 146 known moons, with new discoveries continuing as our observational capabilities improve. The largest moon is Titan, with a diameter of 5,150 kilometers, making it the second largest moon in the solar system after Ganymede. Titan is the only moon with a substantial atmosphere, which is thicker than Earth's atmosphere in terms of surface pressure. Titan's atmosphere is primarily nitrogen, about 98.4%, with about 1.4% methane and traces of other hydrocarbons. The surface pressure on Titan is about 1.5 times Earth's surface pressure at sea level. This thick atmosphere creates a greenhouse effect that keeps Titan's surface temperature at about -179 degrees Celsius, much warmer than it would be without the atmosphere, but still cold enough that water ice is as hard as rock. At these temperatures, methane can exist as a solid, liquid, and gas, just as water does on Earth. Titan has weather patterns driven by methane, with clouds forming in the atmosphere and methane rain occasionally falling to the surface. There are lakes and seas of liquid methane and ethane on Titan's surface, primarily in the polar regions. Radar observations from the Cassini spacecraft map these features in detail, showing coastlines, islands, and what appear to be river channels carved by flowing liquid hydrocarbons. The largest of these seas is called Kraken Mare, located in Titan's North Polar region. It covers an area of about 400,000 square kilometers, larger than the Caspian Sea on Earth. Kraken Mare is filled with liquid methane and ethane, probably with some dissolved nitrogen and other hydrocarbons. The liquid is transparent, and the sea is estimated to be at least 100 meters deep in some locations, possibly much deeper. Titan's surface is also shaped by wind, which creates dune fields near the equator. These dunes are made of hydrocarbon particles that have settled out of the atmosphere, and they can be hundreds of kilometers long, running roughly parallel to each other in the direction of prevailing winds. The landscape of Titan is alien yet strangely familiar, with processes that mirror Earth's hydrological cycle but using completely different materials. Titan orbits Saturn every 15.95 days at a distance of about 1,222,000 kilometers. Like Earth's moon and many other large moons, Titan is tidally locked to Saturn, always showing the same face to the planet. This tidal locking is the stable endpoint of gravitational interactions that occurred over billions of years as Saturn's gravity raised tides in Titan's body, gradually slowing its rotation until the rotation period matched the orbital period. Another notable moon of Saturn is Enceladus, which orbits at a distance of about 238,000 kilometers every 1.37 days. Enceladus is small, only about 500 kilometers in diameter, but it is one of the most geologically active bodies in the solar system. The southern polar region of Enceladus has a series of long cracks called tiger stripes, from which enormous plumes of water vapor and ice particles erupt into space. These plumes were discovered by the Cassini spacecraft in 2005 and have been observed continuously since then. The material erupting from Enceladus contains water, salt, and organic molecules, suggesting that beneath the icy crust lies a global ocean of liquid water. This ocean is kept liquid by tidal heating, similar to the mechanism that heats Europa's ocean. Enceladus is caught in an orbital resonance with another moon, Dione, which maintains Enceladus's slightly elliptical orbit and generates the tidal flexing necessary to heat the interior. The plumes from Enceladus supply material to Saturn's E ring, the outermost and most diffuse of Saturn's rings. As ice particles escape from Enceladus, they go into orbit around Saturn, gradually spreading out to form a faint ring that extends from about 180,000 kilometers to about 480,000 kilometers from the planet. This ring is constantly being replenished by Enceladus, meaning it is not a primordial feature, but a dynamic one sustained by ongoing geological activity. Moving outward from Saturn, we come to Uranus, which orbits at an average distance of about 2.87 billion kilometers from the Sun, or 19.2 AU. Uranus is an ice giant, smaller than Jupiter and Saturn, but still much larger than Earth, with a diameter of about 50,718 kilometers. Uranus is composed primarily of water, methane, and ammonia ices surrounding a small rocky core with an outer atmosphere of hydrogen and helium. The most distinctive feature of Uranus is its extreme axial tilt. While most planets have their axes tilted only modestly relative to the plane of their orbits, Uranus is tilted 98 degrees, meaning it essentially rotates on its side. The planet's north pole points almost directly at the Sun during one season, and then the south pole points at the Sun half a Uranian year later. Since Uranus takes 84 Earth years to orbit the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. The cause of this extreme tilt is unknown, but the most widely accepted hypothesis involves one or more giant impacts early in the solar system's history. Computer simulations suggest that a collision with a body 1 to 3 times the mass of Earth, occurring during the final stages of planetary formation, could have knocked Uranus onto its side. Such an impact would have been catastrophic, releasing enormous energy, but after the debris settled, Uranus would have continued orbiting the Sun in its new orientation, with the tilt preserved over billions of years. Uranus rotates relatively quickly despite its tilt, completing one rotation every 17 hours and 14 minutes. This rotation drives atmospheric winds and weather patterns, though Uranus's atmosphere appears much calmer than Jupiter's or Saturn's. When Voyager 2 flew past Uranus in 1986, it observed a nearly featureless blue-green disk with only a few faint clouds. This apparent calmness may have been due to the viewing angle and the season. Uranus's south pole was pointed almost directly at the Sun at the time, creating unusual atmospheric conditions. More recent observations from Earth-based telescopes and the Hubble Space Telescope have revealed more atmospheric activity on Uranus, including cloud systems and storms. As Uranus has moved along its orbit and the seasons have changed, the illumination has become more complex, and atmospheric dynamics have become more visible. The planet's blue-green color comes from methane in the atmosphere, which absorbs red light and reflects blue and green wavelengths. Uranus has a ring system, though it is much fainter and narrower than Saturn's. The rings were discovered in 1977 during observations of a stellar occultation, when Uranus passed in front of a star as seen from Earth. Astronomers noticed that the star's light dimmed several times, both before and after Uranus itself blocked the star, indicating the presence of rings. We now know of 13 distinct rings around Uranus, all of them narrow and dark, composed of particles that reflect very little light. These rings are quite different from Saturn's bright, icy rings. Uranus's rings contain a higher proportion of dark, carbonaceous material, making them difficult to observe. The particles are also larger on average, ranging from a few centimeters to a few meters across. Uranus has at least 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons orbit in the same highly tilted plane as the rings, perpendicular to the plane of the solar system. Like most large moons, they are tidally locked to Uranus, always showing the same face to the planet. Miranda, the smallest of the 5 major moons, is perhaps the most geologically interesting. Its diameter is only about 472 kilometers, yet its surface shows a remarkable diversity of terrain. There are heavily cratered regions that look ancient, alongside younger regions with parallel grooves and ridges. Some cliffs on Miranda rise as high as 20 kilometers, taller than any cliff in the solar system relative to the size of the body. The cause of this dramatic geology is not entirely understood. One hypothesis is that Miranda was shattered by a massive impact and then reassembled itself under its own gravity, creating the patchwork appearance we see today. The farthest planet from the Sun is Neptune, orbiting at an average distance of about 4.5 billion kilometers or 30 AU. Neptune is slightly smaller than Uranus, with a diameter of about 49,244 kilometers, but it is denser and more massive. Like Uranus, Neptune is classified as an ice giant, composed primarily of water, ammonia, and methane surrounding a rocky core, with an outer atmosphere of hydrogen and helium. Neptune was not discovered through direct observation, but through mathematical prediction. In the mid-1800s, astronomers noticed that Uranus was not following its predicted orbit precisely. The deviation suggested the gravitational influence of another unknown planet beyond Uranus. French mathematician Urbain Le Verrier calculated where this planet should be, and German astronomer Johann Galle found Neptune on his first night of searching in September 1846, very close to the predicted position. This discovery was a triumph of Newtonian physics, demonstrating that the same laws of gravity that govern motion on Earth also apply to the most distant reaches of the solar system. Neptune rotates relatively quickly, completing one rotation in about 16 hours and 7 minutes. Despite being more than 30 times farther from the Sun than Earth and receiving very little solar energy, Neptune has remarkably dynamic weather, with the fastest sustained winds in the solar system reaching speeds as high as 2,100 kilometers per hour. These winds are faster than the speed of sound in Neptune's atmosphere. The energy driving these extreme winds comes primarily from Neptune's interior. Neptune radiates about 2.61 times as much energy as it receives from the Sun. This internal heat, like Jupiter's and Saturn's, comes from gravitational contraction and possibly other processes we do not yet fully understand. The temperature at Neptune's cloud tops approaches 55 Kelvin, which is minus 218 degrees Celsius, making the outer atmosphere one of the coldest places in the solar system. Yet, beneath the clouds, temperatures rise steadily due to internal heat. Neptune's atmosphere is primarily hydrogen and helium, with about 1 to 2% methane. The methane absorbs red light and reflects blue, giving Neptune its distinctive blue color. For many years, images from Voyager 2 made Neptune appear much deeper blue than Uranus, but this was partly due to image processing to enhance cloud features. More recent analysis shows that Neptune and Uranus are actually quite similar in color, both pale blue worlds. When Voyager 2 flew past Neptune in August 1989, it observed a large oval storm system in the southern hemisphere, similar in some ways to Jupiter's Great Red Spot. This feature, called the Great Dark Spot, was about 13,000 kilometers across, roughly the size of Earth. The storm rotated counterclockwise and completed one rotation every 17 days or so. However, when the Hubble Space Telescope observed Neptune in the mid-1990s, the Great Dark Spot had disappeared. Other dark spots have since appeared in Neptune's atmosphere, both in the northern and southern hemispheres, suggesting these storms form and dissipate over timescales of years to decades, unlike Jupiter's more persistent features. Neptune has a ring system, though it is faint and difficult to observe. The rings were confirmed by Voyager 2 in 1989. There are at least 5 main rings, some of which contain bright clumps of material called arcs. The arcs in the outermost ring, the Adam's ring, are gravitationally confined by the moon Galatea, which orbits just inside the ring. This is similar to how shepherd moons maintain the structure of Saturn's rings, though the mechanism in Neptune's case is more complex and still being studied. Neptune has at least 16 known moons. The largest is Triton, with a diameter of about 2,706 kilometers, making it the 7th largest moon in the solar system. Triton is unusual in several ways. It orbits Neptune in a retrograde direction, opposite to Neptune's rotation, which strongly suggests it was not formed along with Neptune, but was captured from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Triton is extremely cold, with surface temperatures around -235 degrees Celsius. Despite these frigid temperatures, Voyager 2 discovered active geysers on Triton's surface, erupting nitrogen ice and dark material up to 8 kilometers high into the thin atmosphere. These geysers are thought to be driven by solar heating of dark material beneath Triton's translucent nitrogen ice surface. Even though sunlight at Neptune's distance is very weak, it is apparently enough to create pressure beneath the ice that occasionally vents dramatically. Triton's surface is geologically young, with relatively few impact craters. Much of the terrain is covered by nitrogen and methane frost. There are regions with a cantaloupe-like texture formed by rising blobs of ice that have disrupted the surface. The surface also shows long fractures and what appear to be frozen lakes of water ice. The combination of these features suggests Triton has been geologically active in the relatively recent past, perhaps driven by tidal heating from Neptune as Triton's orbit gradually circularizes over millions of years. Triton's atmosphere is tenuous but measurable, composed primarily of nitrogen with traces of methane. Observations from Earth show that Triton's atmosphere has been warming slightly over recent decades, though scientists do not yet fully understand why. It is possible this warming is seasonal, related to Triton's long orbital period around Neptune and the slow change in solar illumination patterns, or it could be related to longer-term variations in surface albedo as frosts migrate across the surface. We have now journeyed outward through the solar system, visiting each of the 8 major planets in turn. As we settle into this midpoint of our exploration, it is worth pausing to reflect on what we have encountered so far. We have seen planets that are rocky and dense, planets that are gaseous and massive, planets that rotate quickly and planets that rotate slowly, planets with thick atmospheres and planets with almost none at all. Through all this diversity, certain patterns have emerged. The inner planets, Mercury through Mars, are all relatively small and made primarily of rock and metal. They formed in the warmer regions of the solar nebula, where only materials with high melting points could condense into solid form. Water and other volatile compounds remained mostly in gaseous form in these regions and either drifted outward or were blown away by the young sun's intense radiation and solar wind. The result is 4 compact rocky worlds with thin atmospheres or no atmospheres at all. The outer planets, Jupiter through Neptune, formed in the colder regions of the solar nebula, where water ice could condense and contribute to the solid material available for planet building. This meant there was roughly 4 times as much solid material available to form planets in the outer solar system compared to the inner solar system. Because water is relatively abundant, and ice constitutes a large fraction of the available solids beyond what is called the frost line or snow line, located somewhere around 2.7 to 4 astronomical units from the Sun. With more solid material available, planetesimals in the outer solar system could grow larger more quickly. Once they reached about 10 to 15 Earth masses, their gravity became strong enough to capture and retain hydrogen and helium gas directly from the solar nebula. This gas accretion happened rapidly over perhaps a few 100,000 to a few million years before the solar wind from the young sun dispersed the remaining gas from the solar system. The result is 4 giant planets, each many times more massive than Earth, composed primarily of the same hydrogen and helium that makes up the Sun. These formation processes occurred over a period of about 10 to 100 million years, a very short time compared to the total age of the solar system. A Sun-like star typically takes approximately 1 million years to form, with the protoplanetary disk evolving into a planetary system over the next 10 to 100 million years. After this initial formation period, the solar system has remained relatively stable for the past 4.5 billion years or so, with planets moving in their established orbits, gradually evolving but not changing in fundamental ways. Let us turn now to consider planetary magnetic fields, invisible structures that surround many planets and interact with the solar wind, the constant stream of charged particles flowing outward from the Sun. A magnetic field is generated when electrically conducting material moves in certain patterns, typically involving rotation. In planets, this usually means a liquid metallic core that conducts electricity and rotates along with the planet. The moving conducting fluid generates electric currents, and these currents create magnetic fields through a process called the dynamo effect. Earth has a strong magnetic field generated in its liquid iron outer core. This field extends thousands of kilometers into space, creating a region called the magnetosphere that deflects most of the charged particles in the solar wind away from Earth. When these particles do penetrate the magnetosphere near the magnetic poles, they interact with the gases in the upper atmosphere, creating aurora, the shimmering curtains of light visible at high latitudes. Mercury also has a magnetic field, though much weaker than Earth's. This is somewhat surprising given Mercury's slow rotation. The field suggests that at least part of Mercury's large iron core remains liquid, despite the planet's small size and the expectation that it should have cooled and solidified billions of years ago. The persistence of a liquid core may be due to the presence of lighter elements like sulfur mixed with the iron, which would lower the melting point and allow the core to remain molten longer. Venus and Mars do not have significant global magnetic fields today, though there is evidence that Mars once had a strong field billions of years ago, recorded in the magnetization of ancient rocks. The lack of current magnetic fields suggests these planets either never developed or have since lost the conditions necessary for a dynamo, a liquid conducting rapidly, rotating core. Venus rotates too slowly to generate a significant field, and Mars is too small to have retained enough internal heat to keep its core liquid. The giant planets all have strong magnetic fields. Jupiter's is the strongest in the solar system, about 20,000 times stronger than Earth's at Jupiter's cloud tops. This powerful field creates an enormous magnetosphere that extends millions of kilometers from the planet, well beyond the orbits of the Galilean moons. Charged particles trapped in Jupiter's magnetosphere are accelerated to high energies, creating intense radiation belts that would be lethal to unprotected spacecraft and astronauts. Saturn also has a strong magnetic field, though weaker than Jupiter's. One unusual feature of Saturn's field is that it is very closely aligned with the planet's rotation axis, more so than any other planet. Most planetary magnetic fields are tilted at some angle relative to the rotation axis, but Saturn's tilt is less than 1 degree, making it nearly perfect. This alignment is not fully understood and continues to be a subject of research. Uranus and Neptune both have magnetic fields, but these fields are highly unusual. Unlike other planets, where the magnetic field is roughly aligned with the rotation axis and centered on the planet's core, the magnetic fields of Uranus and Neptune are tilted at large angles to the rotation axis, about 60 degrees for Uranus and 47 degrees for Neptune, and are offset significantly from the centers of the planets. This means the magnetic poles are not near the geographic poles, and as the planets rotate, the magnetic fields wobble and sweep through space in complex patterns. The tilted, offset fields of Uranus and Neptune may result from the structure of their interiors. Instead of being generated in a spherical core, the fields may be generated in relatively thin shells of conducting fluid in the outer portions of the ice layers, where high pressures and temperatures create a state of matter that conducts electricity. This would naturally produce a field that is not centered or aligned with the planet. When the solar wind encounters a planetary magnetic field, the interaction creates the magnetosphere, a region where the magnetic field dominates over the solar wind. The boundary between the magnetosphere and the solar wind is called the magnetopause. Inside the magnetosphere, charged particles from the solar wind can become trapped and spiral along magnetic field lines, creating radiation belts, and when they collide with atmospheric gases near the poles, aurora. Aurora have been observed on Earth, Jupiter, Saturn, Uranus, and Neptune. Observations combining visible light images from the Hubble Space Telescope with near-infrared images from the James Webb Space Telescope revealed aurora on Neptune for the first time in March 2025. These observations detected trihydrogen cations, a clear indicator of auroral activity. On Neptune, the unusual magnetic field means aurora appear primarily at mid-latitudes rather than near the poles, unlike the polar aurora on Earth. The presence of magnetic fields and magnetospheres is not just scientifically interesting, it has practical implications for understanding planetary environments. A strong magnetic field can shield a planet's atmosphere from erosion by the solar wind. Earth's magnetic field has helped preserve our atmosphere over billions of years. Mars, lacking a global field, has gradually lost much of its atmosphere to space, stripped away by the solar wind. This process continues today, and it may be one reason Mars has such a thin atmosphere compared to Earth and Venus. Now let us consider rotation in more detail, exploring the different rates at which planets spin and how this affects their structure and appearance. We have already mentioned that different planets rotate at different rates, from Mercury's leisurely 58.6 Earth days to Jupiter's rapid 9 hours and 55 minutes. These rotation rates are not arbitrary. They result from the angular momentum that each planet inherited from the solar nebula during formation, modified by tidal interactions and, in some cases, giant impacts. Angular momentum is a property of rotating objects that depends on mass, size, and rotation speed. In the absence of external forces, angular momentum is conserved, meaning it cannot be created or destroyed, only transferred. When the solar nebula collapsed to form the solar system, it was rotating slowly. As it contracted, conservation of angular momentum required it to spin faster, just as a figure skater spins faster when pulling their arms inward. The material that formed each planet carried some of this angular momentum, giving each planet its initial rotation. Over billions of years, tidal interactions can modify rotation rates. We have already discussed how Earth's rotation is gradually slowing due to tidal forces from the Moon, and how many moons have become tidally locked to their planets. The giant planets rotate quickly, partly because they are massive and formed from large amounts of rotating material, and partly because they have experienced less tidal slowing than smaller planets. Their moons are relatively small compared to the planets themselves, so the tidal forces are weaker and the slowing is less pronounced. The different rotation rates create different shapes. Rapidly rotating planets bulge at the equator due to centrifugal force. Jupiter's equatorial bulge is easily visible even in small telescopes. The difference between the equatorial and polar diameters is about 9,300 kilometers, or about 7% of the average diameter. Saturn's bulge is even more pronounced, about 10%, making it the most oblate planet in the solar system. The slower rotating terrestrial planets have much smaller bulges, barely measurable in most cases. Rotation also affects internal structure and heat distribution. On Jupiter and Saturn, the rapid rotation organizes atmospheric circulation into bands parallel to the equator, as we have seen. Heat from the interior rises in certain zones and sinks in others, creating stable patterns that persist for decades or longer. On slower rotating worlds like Venus, atmospheric circulation is more complex and less organized into east-west bands. Let us now consider day length, which is related to rotation but not identical. A day is defined as the time from one sunrise to the next sunrise, which depends on both the planet's rotation and its orbital motion around the Sun. On Earth, the rotation period is 23 hours, 56 minutes, and 4 seconds relative to the stars, but the solar day, from noon to noon, is 24 hours, because Earth moves along its orbit during one rotation, requiring extra time to bring the Sun back to the same position in the sky. For planets with fast rotation and slow orbital motion, the rotation period and day length are nearly the same. Mars, for example, rotates every 24 hours and 39 minutes relative to the stars, and its solar day is only slightly longer, about 24 hours, 39 minutes, and 35 seconds. The difference is minimal because Mars's orbital period is long compared to its rotation. For slow rotating planets, the situation is more complex. Venus takes 243 Earth days to rotate once on its axis, the slowest rotation of any planet, and its rotation is retrograde, opposite to its orbital direction. Venus orbits the Sun in about 224.7 Earth days. The combination of slow retrograde rotation and orbital motion creates a solar day on Venus of 117 Earth days. This means sunrise to sunrise on Venus takes 117 Earth days, but the planet rotates relative to the stars every 243 days in the backward direction. Mercury's situation is even stranger. Mercury rotates every 58.6 Earth days, but orbits the Sun every 88 Earth days. The ratio is not random. Mercury's rotation is locked in a 3:2 resonance with its orbit, as we discussed earlier. Because of this resonance, one solar day on Mercury, from sunrise to sunrise, lasts 176 Earth days, which is exactly 2 Mercurian years. The giant planets all have relatively simple relationships between rotation and day length, because they rotate quickly and orbit far from the Sun. Jupiter's day is essentially the same as its rotation period, about 9 hours and 55 minutes. The same is true for Saturn, Uranus, and Neptune. Their rapid rotations dominate over their slow orbital motions, so the solar day and the rotation period are nearly identical. These different day lengths would create very different experiences of time on each world. On Jupiter, the Sun would cross the sky in less than 5 hours from rise to set. On Saturn, slightly longer. On Mercury, the Sun would hang in the sky for months, moving imperceptibly slowly, occasionally reversing direction due to Mercury's elliptical orbit and resonant rotation. On Venus, the Sun would rise in the west and take almost 2 months to cross the sky to set in the east. Now let us consider how planets have evolved over deep time, the billions of years since their formation. The solar system is approximately 4.6 billion years old, and the planets have existed for nearly that entire span. During this time, they have cooled, solidified, cratered, eroded, and in some cases remained geologically active. Understanding this evolution helps us see planetary features not as static characteristics, but as snapshots in an ongoing process. The initial collapse of the solar nebula took about 100,000 years. After that time, the young Sun reached a surface temperature similar to that of a main sequence star. Accretion of gas onto the star continued for another 10 million years before the disk dispersed. During this time, planetesimals were colliding and growing into larger bodies. The terrestrial planets formed through continued collisions of planetesimals and protoplanets, a process that took perhaps 50 to 100 million years to complete. The final stages of terrestrial planet formation were violent. Large impacts were common as the last protoplanets collided and merged. Earth's moon is thought to have formed from debris ejected when a Mars-sized body collided with the proto-Earth about 4.5 billion years ago, early in Earth's history. This impact would have been catastrophic, vaporizing rock and creating a temporary ring of debris around Earth that eventually coalesced into the moon. After the main accretion phase, the planets entered a period called the Late Heavy Bombardment, approximately 4 billion to 3.8 billion years ago, during which the inner solar system experienced an intense period of impacts. This bombardment may have been caused by gravitational perturbations from the giant planets, which caused icy bodies from the outer solar system to migrate inward and collide with the terrestrial planets. The cratered surfaces of the Moon, Mercury, and Mars still record this ancient pummeling. Since the late heavy bombardment, the inner planets have evolved more quietly. Mercury and the Moon, being small and lacking atmospheres, have remained essentially unchanged for billions of years. Their surfaces record impacts accumulated over the entire history of the solar system. Venus and Earth, being larger and more geologically active, have erased much of their ancient impact history through volcanism and, in Earth's case, plate tectonics and erosion. Mars represents an intermediate case. It was geologically active early in its history, with volcanoes and flowing water reshaping parts of the surface. However, being smaller than Earth, Mars cooled more quickly and its geological activity declined over time. The last major volcanic eruptions on Mars may have occurred only a few 100 million years ago, which is recent in geological terms, but still ancient by human standards. Most of Mars's surface, however, is billions of years old, preserving a record of the planet's early, more active period. The giant planets have evolved differently. They do not have solid surfaces to record impacts, and their internal heat keeps them active even billions of years after formation. Jupiter and Saturn are still slowly contracting and radiating heat, just as they have been since formation. This process will continue for billions of years more, though at an ever-decreasing rate as they gradually cool. Uranus presents a puzzle. It radiates only 1.1 times as much energy as it receives from the Sun, much less than Neptune's 2.61 times, despite being similar in size and structure. Why Uranus emits so little heat compared to Neptune is not fully understood. One possibility is that its interior is stratified, with layers that do not mix efficiently, trapping heat deep inside where it cannot radiate away. This stratification might have resulted from the giant impact that tilted Uranus onto its side. The moons of the giant planets have their own evolutionary histories. Some, like Jupiter's Europa and Saturn's Enceladus, remain geologically active today, powered by tidal heating. Others, like Callisto and most of Saturn's mid-sized moons, are ancient and cratered, having been geologically dead for billions of years. Titan continues to have an active methane cycle, with methane rain carving channels and filling lakes, though on timescales much slower than Earth's water cycle. The orbits of the planets themselves have also evolved over time. Early in the solar system's history, the giant planets were likely in different positions than they are today. 1. Widely discussed model, called the Nice model after the city in France where it was developed, proposes that Jupiter, Saturn, Uranus, and Neptune all migrated from their original orbits to their current positions sometime between 400 million to 800 million years after the solar system formed. According to this model, Jupiter migrated slightly inward, while Saturn, Uranus, and Neptune migrated outward. This migration was driven by gravitational interactions with a disk of planetesimals remaining in the outer solar system. As the planets moved, they gravitationally scattered these planetesimals, some into the inner solar system, where they contributed to the late heavy bombardment, and others outward into the Oort cloud, a spherical shell of icy bodies that extends halfway to the nearest star. This migration had profound effects on the solar system. It may explain why Uranus and Neptune are where they are today, far from the Sun in orbits that are difficult to reach, through normal accretion in the sparse outer solar nebula. It may explain the late heavy bombardment. It may explain the structure of the asteroid belt and the Kuiper belt, and the orbits of irregular moons and Trojan asteroids that share orbits with planets. The Nice model is still being tested and refined as new observations and simulations provide more data, but it represents a shift in thinking about planetary orbits from static to dynamic, from fixed to evolving. The planets may appear permanent and unchanging on human timescales, but over millions and billions of years, even their orbits can shift and change. Looking forward, what will happen to the planets in the future? Over the next few billion years, the solar system will continue much as it has for the past few billion years. The planets will orbit, rotate, cool, and evolve geologically at rates so slow they are imperceptible on human timescales. Impact rates will continue to decline as the remaining population of Asteroids and comets gradually diminishes through ejection and collision. Earth's moon will continue to drift away from Earth, and Earth's rotation will continue to slow until eventually, in billions of years, Earth becomes tidally locked to the moon, just as the moon is already locked to Earth. At that point, one side of Earth will always face the moon, and the moon will hang motionless in the sky as seen from that hemisphere, forever invisible from the other hemisphere. Mars will likely remain cold and dry, though some models suggest it could experience brief warming periods if its axial tilt changes significantly due to gravitational perturbations from other planets. Mars's tilt is less stable than Earth's because Mars lacks a large moon to stabilize it. Over millions of years, the tilt can vary from about 10 degrees to 60 degrees, compared to Earth's stable 23.5 degrees, held steady by the moon. The giant planets will continue to cool and contract very slowly. Jupiter will still be radiating more heat than it receives from the Sun even 1 trillion years from now, though the excess will be smaller and smaller. The moons will continue their slow orbital evolution, with tidal interactions gradually changing their orbits and rotation states over immense timescales. The most dramatic change awaiting the solar system will occur in about 5 to 7 billion years, when the Sun exhausts the hydrogen fuel in its core and begins to evolve into a red giant star. During this phase, the Sun will expand dramatically, possibly engulfing Mercury and Venus. Earth may or may not be swallowed, depending on how much mass the Sun loses during its expansion and how that affects Earth's orbit. Even if Earth escapes being engulfed, it will be sterilized by the intense heat from the nearby, vastly expanded Sun. The oceans will boil away, the atmosphere will be stripped, and the surface will become molten. Mars may warm enough to have liquid water briefly on its surface, though any such period would be short-lived in cosmic terms. The giant planets will be largely unaffected by the Sun's red giant phase, being far enough away to avoid the worst effects. However, their icy moons may warm significantly. Europa, Enceladus, and Titan might experience dramatic increases in temperature, potentially creating habitable conditions in their subsurface oceans, though only for a few 100 million years before the Sun contracts into a white dwarf and the solar system cools permanently. As a white dwarf, the Sun will gradually fade over trillions of years, cooling and dimming until it becomes a cold, dark stellar remnant. The planets will continue to orbit this dead star, frozen and lifeless, preserved as monuments to a solar system that once harbored warmth and light, and, on at least one world, life. This far future is so distant that it is almost incomprehensible. The span of time from now until the Sun becomes a red giant is longer than the entire age of the solar system to date. We are, in a sense, living in the early chapters of the solar system's story, during its long, stable middle age, when the planets orbit reliably and the Sun shines steadily. Now let us turn to consider light and distance, exploring how sunlight appears different on each world and what the sky looks like from different planetary surfaces. These details are not often discussed, but they contribute to the distinct character of each planet and help us imagine what it might be like to stand on another world. Sunlight intensity decreases with the square of the distance from the Sun. At Earth's distance of 1 AU, we receive a certain amount of solar energy per square meter. At twice the distance, we would receive 1/4 as much. At 10 times the distance, we would receive 1/100th as much. This relationship is fundamental to understanding the lighting conditions on other planets. Mercury, at an average distance of about 0.4, Au from the Sun receives about 6.7 times as much sunlight per square meter as Earth does. The Sun appears more than twice as large in Mercury's sky as it does from Earth. High noon on Neptune would seem like dim twilight to us, with sunlight roughly 900 times less bright than on Earth. On Venus, at about 0.7 AU, sunlight is almost twice as intense as on Earth, though you would never see the Sun directly from Venus's surface due to the thick cloud cover. The clouds reflect much of the incoming sunlight back to space, which is why Venus is so bright when viewed from Earth. Below the clouds, the surface is illuminated by a diffuse, orange-tinted light filtered through the thick atmosphere. Mars, at 1.5 AU, receives about 44% as much sunlight as Earth. The Sun appears smaller in the Martian sky, and the light is noticeably dimmer, though not so dim that human vision would be impaired. The Martian sky is typically butterscotch, or salmon-colored during the day due to fine dust suspended in the atmosphere. At sunset and sunrise, the sky near the Sun becomes bluish, the opposite of Earth's red sunsets. This happens because dust particles scatter blue light forward, toward the observer, rather than scattering it away as molecules in Earth's atmosphere do. At Jupiter, 5.2 AU from the Sun, sunlight is about 4% as intense as at Earth, or roughly 1/25. The Sun appears much smaller, about 1/5 its apparent size from Earth. From Jupiter's cloud tops, the Sun would still be bright enough to cast shadows, but the overall illumination would be dim, comparable perhaps to a heavily overcast day on Earth. Jupiter's bands and zones would be visible, the great red spot a prominent dark oval against the lighter zones. From Saturn, at 9.5 AU, sunlight is roughly 1% as intense as on Earth. The Sun would appear as a very bright star, noticeably brighter than any planet. Appears from Earth, but clearly much smaller and dimmer than the Sun we know. The rings would be spectacularly visible from Saturn's cloud tops, depending on latitude and the orientation of the rings. At certain times and locations, the rings would stretch across the sky, a brilliant arc of ice particles reflecting sunlight. Uranus, at 19.2 AU, receives only about 0.3% of Earth's sunlight, or 1/300th. The Sun would be a brilliant point of light, but far smaller than we are used to. The pale blue-green clouds would be barely illuminated, visible primarily in long-exposure photographs or enhanced images. The sky would appear dark even during daytime, with stars visible all around the Sun. Neptune, at 30 AU, experiences the dimmest sunlight of any planet. Sunlight at Neptune is roughly 900 times less bright than on Earth, about 0.1% of Earth's intensity. The Sun appears as an extremely bright star, but one that clearly does not dominate the sky. Neptune's blue clouds would be dimly lit, and the overall impression would be of perpetual deep twilight. From the surface of Triton, looking back toward Neptune, you would see the planet as a large blue disk, about 30 times the apparent diameter of the Moon as seen from Earth, hanging motionless in the sky due to Triton's tidal locking. The Sun would be a brilliant point of light far away, providing enough illumination to see by, but creating an environment of profound dimness compared to the inner solar system. From each world, other planets would be visible in the sky, though their appearance would vary greatly. From Mercury, Venus would occasionally shine brilliantly, and Earth would be a blue point of light visible near the Sun during certain parts of Mercury's long day. From Mars, Earth would appear as a bright bluish star, and Jupiter would be easily visible, the brightest object in the Martian night sky besides the two small moons, Phobos and Deimos. From Jupiter, The 4 Galilean moons would move across the sky in a complex dance. Io would orbit fastest, completing one circuit every 42 hours or so relative to Jupiter's rapid rotation. Europa, Ganymede, and Callisto would follow in slower procession. Eclipses and transits would be frequent, with moons casting shadows on the cloud tops and occasionally passing in front of each other as seen from Jupiter. From Saturn, the view would be dominated by the rings, visible from most latitudes as a vast arc stretching across the sky. The rings would appear bright when illuminated by the sun and would cast shadows on the planet's cloud tops. Titan, Saturn's largest moon, would be easily visible with the naked eye, though its thick atmosphere would hide its surface features. From Uranus, the moons would orbit in the same unusual tilted plane as the planet's equator, perpendicular to the orbital plane. This would create a unique sky where moons appear to orbit vertically rather than horizontally as they do for most planets. The sun would rise and set at the poles, spending 42 years continuously above the horizon, then 42 years below, creating the strangest seasons in the solar system. From Neptune, Triton would move backward across the sky, retrograde to Neptune's rotation, completing one orbit every 5.8 days. The view of the distant sun and the other planets would be similar to Uranus, though Neptune is even farther from everything, truly at the edge of the known solar system before the vast expanse leading to the Kuiper Belt and beyond. These perspectives remind us that the solar system is a diverse collection of worlds, each with its own character and conditions. The constancy we observe from Earth, the regular motions and predictable positions of the planets, exists everywhere, but the experience of that constancy would be radically different depending on where you stood. We are approaching the end of our journey through the solar system. But before we close, let us spend some time with a few more facts that have a particularly calming quality to them. Details about planetary science that emphasize patience, persistence, and the reassuring predictability of natural law. Consider the orbits themselves, the paths that planets follow around the sun. These paths are ellipses, a geometric shape discovered by Johannes Kepler in the early 1600s, after years of painstaking analysis of planetary positions recorded by Tycho Brahe. An ellipse has 2 points inside it called foci, and the sum of the distances from any point on the ellipse to the 2 foci is constant. For planetary orbits, the sun sits at one focus and the other focus is empty, just a point in space. The shape of an ellipse is described by a number called eccentricity, which ranges from 0 for a perfect circle to values approaching 1 for very elongated ellipses. Most planetary orbits have low eccentricities, meaning they are nearly circular. Earth's orbit has an eccentricity of about 0.017, meaning the difference between Earth's closest approach to the Sun and its farthest distance is only about 3% of the average distance. This near circularity means Earth receives relatively uniform solar energy throughout the year, with seasons driven primarily by axial tilt rather than distance from the Sun. Mercury has the most eccentric orbit of any planet, with an eccentricity of 0.206. This means Mercury's distance from the Sun varies from about 46 million kilometers at closest approach to about 70 million kilometers at farthest distance, a variation of about 52%. This variation affects Mercury's orbital speed. When Mercury is closest to the Sun, it moves fastest, traveling about 59 kilometers per second. When it is farthest, it slows to about 39 kilometers per second. This variation in speed creates the brief retrograde motion of the Sun across Mercury's sky that we mentioned earlier. The other planets have eccentricities between these extremes. Venus has the most circular orbit after Earth, with an eccentricity of only 0.007. Mars is more eccentric at 0.093, which contributes to its unequal seasonal lengths. The giant planets all have relatively low eccentricities, with Jupiter at 0.049, Saturn at 0.054, Uranus at 0.047, and Neptune at 0.009. These eccentricities are not fixed forever. They vary slowly over tens of thousands to millions of years due to gravitational perturbations from other planets. Earth's eccentricity varies between about 0.0005 and 0.058 over a cycle lasting approximately 100,000 years. These variations affect the amount of solar radiation Earth receives and contribute to long-term climate cycles, including ice ages. Similar variations occur in other planets' orbits, creating complex long-period cycles in solar system dynamics. Kepler's second law states that a line connecting a planet to the Sun sweeps out equal areas in equal times. This means that when a planet is closer to the Sun and moving faster, it covers a greater distance along its orbit, and when it is farther and moving slower, it covers less distance. Yet, the area swept out by that imaginary line remains constant. This is a consequence of conservation of angular momentum, and it applies to every orbit in the solar system, from planets to moons to asteroids and comets. Kepler's third law relates the orbital period of a planet to its average distance from the Sun. Specifically, the square of the orbital period is proportional to the cube of the average distance. This relationship means that if you know how far a planet is from the Sun, you can calculate how long it takes to orbit, and vice versa. For instance, if a planet orbits at 4 AU, 4 times Earth's distance, its orbital period would be the square root of 4 cubed, which is 8 years. This mathematical relationship is not a coincidence or an approximation. It is an exact consequence of Newton's law of universal gravitation, which states that the gravitational force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton showed that Kepler's empirical laws could be derived from this more fundamental principle, unifying terrestrial and celestial mechanics into a single framework. The precision of these laws allows us to predict planetary positions with remarkable accuracy. Astronomers can calculate where Mars will be 1,000 years from now to within a few kilometers. They can calculate the exact time of solar eclipses decades in advance, knowing precisely when the moon's shadow will cross specific locations on Earth's surface. This predictability is comforting. It means the solar system operates according to comprehensible rules, not chaos or whim. Let us consider some of the quieter aspects of planetary surfaces and how they change over geological time. Crater counts on planetary surfaces provide a way to estimate the age of different regions. The more craters a surface has, the older it is, because craters accumulate over time as impacts occur. By counting craters in images and comparing the counts to estimates of impact rates, planetary geologists can determine that some regions of Mars are more than 3 billion years old, while others are perhaps only a few 100 million years old. The process is not perfect. Impact rates have changed over time, declining steeply after the late heavy bombardment and then declining more gradually since. Smaller craters erode and fill in over time, especially on bodies with atmospheres or geological activity. Large craters persist longer but can be buried by lava flows or covered by wind-blown dust. Despite these complications, crater counting remains one of the most important techniques for understanding planetary surface ages. On the Moon, which has no atmosphere or geological activity to erase craters, the surface records the entire impact history of the inner solar system. The dark regions called Maria, Latin for seas, are lava flows that filled in large impact basins between about 3.9 and 3.1 billion years ago. These Maria have far fewer craters than the brighter highlands, which are the oldest parts of the lunar surface, dating back to the Moon's formation about 4.5 billion years ago. Mercury's surface is similar to the Moon's, heavily cratered and ancient, but with some differences. Mercury has large scarps, cliffs that run for hundreds of kilometers across the surface. These scarps formed as Mercury's interior cooled and contracted, causing the crust to buckle and thrust upward in some places. The largest scarp, Discovery Rupees, is about 650 kilometers long and rises about 3 kilometers above the surrounding terrain. These scarps are old, dating to early in Mercury's history when the contraction was most rapid. Mars has a dichotomy in its surface, with the northern hemisphere much smoother and lower in elevation than the southern hemisphere. The northern plains are relatively young, perhaps 3 to 4 billion years old, with fewer craters and evidence of past water flow. The southern highlands are older, heavily cratered, and more like the Moon or Mercury. The boundary between these two regions is sharp in some places and gradual in others, and the cause of this hemispheric difference is still debated. Hypotheses include a giant impact that resurfaced the northern hemisphere, or different volcanic and erosional processes that operated differently in the two hemispheres. Venus's surface is relatively young, probably less than 1 billion years, old on average, with some regions even younger. The entire surface appears to have been resurfaced by volcanic activity at some point, erasing whatever older craters existed. Since then, new craters have accumulated, and we can count them to estimate ages. Venus has about 1,000 impact craters larger than 1 kilometer in diameter, compared to hundreds of thousands on Mars or millions on the Moon. This lower crater density indicates a younger surface. The volcanic resurfacing of Venus may have happened catastrophically, with the entire planet undergoing a period of intense volcanism over a relatively short time, or it may have happened gradually, with different regions resurfaced at different times. The data from Magellan, the spacecraft that mapped Venus in the early 1990s, supports both models to some extent, and the question remains open. All of these surface processes operate on timescales vastly longer than human experience. A crater forms in seconds during an E1 impact, but the cratered landscape accumulates over millions to billions of years. Volcanic flows may erupt over days to years, but the volcanic plains they create represent millions of years of accumulated eruptions. Scarps form as planets contract over hundreds of millions of years. Even fast processes like wind erosion take millions of years to sculpt landscapes on airless or nearly airless bodies. This slow pace is part of what makes planetary geology calming to contemplate. Nothing is rushed. Changes happen, but they happen with a patience that makes human timescales seem almost instantaneous by comparison. A mountain on Mars has stood for billions of years and will stand for billions more. A crater on the Moon has preserved its shape for 3 billion years, and if nothing disturbs it, it will remain for 3 billion more. Let us turn finally to consider the atmospheres of planets once more, but now focusing on their long-term stability and evolution. An atmosphere is held to a planet by gravity. The strength of a planet's gravity depends on its mass and radius. A planet with strong gravity can hold on to lighter gases like hydrogen and helium, while a planet with weaker gravity can only retain heavier gases like nitrogen, oxygen, and carbon dioxide. Very small bodies like asteroids and small moons cannot retain atmospheres at all because their gravity is too weak. The temperature of the atmosphere also matters. Gas molecules in a hot atmosphere move faster on average than those in a cool atmosphere. If molecules move fast enough to exceed the escape velocity of the planet, they can leave the atmosphere and drift into space. This process, called thermal escape, occurs gradually over millions to billions of years. Earth's atmosphere has evolved dramatically over its history. The early atmosphere was probably composed mainly of hydrogen and helium, captured directly from the solar nebula, but this primordial atmosphere was lost early on, blown away by the intense solar wind from the young sun. A secondary atmosphere then formed from gases released by volcanic activity, primarily water vapor, carbon dioxide, nitrogen, and small amounts of other gases. Over time, water vapor condensed to form the oceans, and carbon dioxide was absorbed into rocks and eventually into living organisms, leaving nitrogen and oxygen as the dominant gases. The oxygen in Earth's atmosphere is almost entirely a product of life. Photosynthetic organisms, first cyanobacteria and later plants, release oxygen as a byproduct of converting sunlight, water, and carbon dioxide into organic compounds. This process has been ongoing for at least 2.4 billion years, gradually transforming Earth's atmosphere from one with almost no free oxygen to the oxygen-rich atmosphere we breathe today. Mars's atmosphere has also evolved, but in a different direction. Early Mars likely had a thicker atmosphere and liquid water on its surface, evidenced by ancient valley networks and lake beds visible in images. However, Mars lost much of its atmosphere over time through a combination of solar wind stripping, chemical reactions with surface rocks, and thermal escape. The loss was accelerated by the absence of a global magnetic field to shield the upper atmosphere from the solar wind. Current measurements from spacecraft orbiting Mars show that atmospheric loss continues today, though at a much slower rate than in the distant past. NASA's MAVEN spacecraft, which has been studying Mars's upper atmosphere since 2014, measures how ions are stripped away by the solar wind and estimates current loss rates. While significant by human standards, these rates are slow enough that changes would take millions of years to noticeably alter the atmospheric pressure. Venus's atmosphere is thought to have evolved through a runaway greenhouse effect. Early Venus may have had liquid water oceans similar to Earth, but being closer to the Sun, it received more solar radiation. This caused more water to evaporate, and water vapor is a greenhouse gas, trapping heat and causing further warming. Eventually, the oceans evaporated completely. Water vapor was broken apart by ultraviolet light, and hydrogen escaped to space while oxygen reacted with surface rocks. Carbon dioxide, released by volcanism and unable to be absorbed into oceans that no longer existed, accumulated in the atmosphere, creating the thick, hot atmosphere Venus has today. This process is mostly in the past, with Venus's atmosphere now in a relatively stable state. The extreme conditions, 92 times Earth's atmospheric pressure and temperatures hot enough to melt lead, will persist indefinitely into the future unless some major external event disrupts the planet. The giant planets have retained their primordial atmospheres of hydrogen and helium because they are massive enough and cold enough to hold on to these light gases. Their atmospheres have evolved. Chemically, with complex organic molecules forming in the upper layers and sinking into the depths. But the bulk composition has remained essentially unchanged since formation. This atmospheric stability, maintained for over 4 billion years, will continue for billions of years into the future. The various moons with atmospheres also show different evolutionary paths. Titan's atmosphere is thick and nitrogen-rich, probably the result of ammonia in Titan's interior being broken down into nitrogen and hydrogen over billions of years. The hydrogen escaped to space while the nitrogen accumulated. Methane in Titan's atmosphere is constantly being destroyed by solar ultraviolet light and cosmic rays, yet it persists, suggesting a reservoir somewhere, possibly in subsurface liquid reservoirs or clathrates, that replenishes the atmospheric methane. Triton has a tenuous atmosphere of nitrogen that may undergo seasonal changes as nitrogen ice at the poles sublimates and refreezes over Triton's long seasonal cycle. Io has an atmosphere that appears and disappears depending on volcanic activity, composed mainly of sulfur dioxide released by volcanoes. When volcanoes are active, the atmosphere thickens. When activity quiets, much of the atmosphere freezes onto the surface. These atmospheric variations occur over timescales from hours to millions of years, creating layers of change. Some processes operate quickly, like weather systems that develop and dissipate in days. Others operate slowly, like the gradual loss of atmosphere to space or the slow accumulation of gases from volcanic outgassing. The overall impression is one of dynamic equilibrium, with atmospheres constantly adjusting to maintain balance between sources and sinks of various gases. Throughout this journey, we have seen planets and moons that are diverse in almost every measurable way, yet all governed by the same fundamental physical laws. Gravity holds them in their orbits, shapes their structures, generates heat through tidal forces, and creates magnetic fields through dynamo processes. Thermodynamics drives the flow of heat from hot interiors to cold space, powering geological activity and atmospheric circulation. Conservation laws of energy, momentum, and angular momentum constrain how systems evolve over time. These laws are not suggestions or approximations. They are precise mathematical relationships that can be tested, verified, and relied upon. When Kepler's laws predict that Jupiter will reach opposition, appearing directly opposite the Sun in Earth's sky, on a specific date, it does. When Newton's laws predict the trajectory of a spacecraft on its way to Saturn, the spacecraft arrives exactly where and when predicted. When thermodynamics predicts how much heat a planet should radiate based on its internal energy, measurements confirm the predictions. This reliability is the foundation of our understanding of the solar system. It is what allows us to send spacecraft across billions of kilometers and have them arrive at their destinations years later, having traveled through space they have never visited, to rendezvous with planets they have never seen, all based on calculations made on Earth using the same physics that governs everything from falling apples to orbiting planets. It is also what allows us to project forward and backward in time with confidence. We can calculate that a solar eclipse will occur on a specific date centuries from now, and we can be certain that it will. We can calculate that a particular configuration of planets occurred thousands of years ago, and we can be certain that it did. This kind of certainty is rare in our experience. Most things in life are uncertain, contingent, unpredictable. Planetary motion is none of these things. As we bring this exploration to a close, think about what we have covered. We began with the inner planets, small and rocky, baked by the nearby sun or covered in thick clouds. We moved outward through the asteroid belt to the giant planets, massive worlds of gas and ice with complex weather systems and extensive moon systems. We considered rotation, magnetic fields, atmospheres, surfaces, craters, volcanism, and all the various processes that shape these worlds. Throughout, the emphasis has been on facts that inspire calm rather than excitement, wonder rather than urgency. The Great Red Spot has rotated in place for centuries and will continue for who knows how long. Titan's methane lakes fill and evaporate on timescales of thousands of years. Olympus Mons stands 22 kilometers high, built up by lava flows spread over millions of years, and it will stand for millions more. The rings of Saturn orbit the planet, each particle in its own path, governed by gravity, colliding gently with neighbors, settling into a thin plane that has existed for possibly hundreds of millions of years and will continue to exist until tidal forces eventually cause it to spiral. Inward or gravitational perturbations disrupt it. These are not stories of drama and conflict. They are stories of patience and persistence. They are reminders that not everything in the universe operates on human timescales, subject to human emotions and motivations. Some things simply exist, governed by natural law, moving through space at speeds determined by gravity, rotating at rates determined by angular momentum, glowing with light that has traveled for minutes or hours or years to reach them. There is a peace in contemplating these facts. It is the peace of knowing that while our personal lives may be full of change and uncertainty, the larger universe continues in patterns that are ancient and enduring. The planets were here long before any human looked up at the night sky, and they will be here long after the last human has ceased to look. This is not a melancholy thought. It is a liberating one. Our struggles and worries, as real as they are to us, exist against a backdrop of cosmic constancy that neither knows nor cares about them. That simply is, existing in a state of elegant motion governed by laws that are, in their own way, beautiful. If you have stayed with me until now, I thank you for your patience and your curiosity. Whether you have listened actively, absorbing information and building mental images of distant worlds, or whether you have let the words become a gentle background as you rested or drifted towards sleep, I hope this journey has provided something of value. Perhaps it has been information, perhaps relaxation, perhaps simply a different perspective on the solar system and our place within it. If you found this exploration worthwhile, I invite you to subscribe to this channel. There are many more topics to explore in astronomy and space science, many more facts that share this quality of quiet fascination, many more journeys we can take together through the cosmos. Subscribing helps this channel grow and tells me that this content is resonating with you, that there is an audience for deep, thorough explorations of astronomical topics delivered in a calm, unhurried way. You can also like this video if it met your expectations or exceeded them. Likes are helpful for letting others know that the content is worth their time. And if you have thoughts, corrections, or topics you would like to see covered in future videos, the comment section is always open. I read comments and take suggestions seriously, and many future videos will come directly from requests and ideas shared by viewers like you. Until next time, I wish you clear skies, peaceful thoughts, and restful sleep. The planets will continue their ancient orbits, the stars will continue their slow drift across the night sky, and the universe will continue to exist in all its patient, magnificent complexity. Thank you for being here, and good night.